Hello class, and welcome to Physics 203 Class 10. This class is on the Bohr model, and this is a continuation of our transition from classical to quantum physics. And the Bohr model specifically was a combination of what we looked at in the last class, the instability of the solar system model combined with the spectrum of hydrogen, okay, which we looked at in earlier classes. And so the Bohr model was kind of a synthesis of classical and quantum ideas and a stepping stone between classical physics and fully quantum physics, which we'll look at in a few weeks. So Bohr's challenge and his goal as he faced physics in the early 20th century was he realized that there was an instability in the solar system model, that the electron would radiate energy as it spiraled around the nucleus, and therefore we have the death spiral of the electron, so to speak. And so he wanted to create a model of the atom that was stable, because clearly atoms didn't just implode on themselves, and which incorporated Planck's new constant H, which he was aware of from the photoelectric effect and from blackbody radiation, and also connected somehow to the intrinsic size of the hydrogen atom. And he wanted to create a model of the atom in such a way that reproduced all of the spectral lines of hydrogen. You remember from our class on spectral lines, we have the visible Balmer series, the infrared Paschen series, and the ultraviolet Lyman series. And so he came up with four postulates, as I mentioned before, kind of a mixture of classical and quantum physics. And here were the postulates that he came up with. He said there were stationary states with definite total energy, which exist in atoms, and which do not radiate electromagnetic energy. And he didn't explain how this was possible. He just said that this was how things must work. By evidence, atoms do not implode and self-destruct, so this must be a new principle. So this was a new quantum principle of these stationary states where electrons existed but were not radiating away their energy. The second was that emission or absorption of light occurs in transitions between these stationary states. Let's call them state 1 and state 2. And when there's a transition between stationary states, energy comes in the form of photons, packets of light, with an energy given by the difference, E1 minus E2, between the two stationary states. And that connects to the light frequency through E, the same formula as Planck's formula. E is equal to hf, where h was Planck's constant, which had already been established, as I said, in several other experiments. So that was a new quantum idea, the idea that that's how atoms radiated by transitioning between these energy states. Third, dynamical quantities like the radius of the electron, the velocity of the electron, and the acceleration of the electron in the hydrogen atom would follow classical laws within a stationary state. So if they're in a stationary state, Newton's laws and the laws of electromagnetism would apply. But those laws couldn't explain what happened during the transitions between the stationary states. Something else was going on, as yet unknown, some new quantum phenomenon. So I'll count this as an old classical postulate, since it's asserting classical relationships between radius, velocity, and acceleration. And fourth, he said that the angular momentum of a stationary state with a circular orbit, he assumed all orbits were circular, was a multiple of Planck's constant h over 2 pi, which is also known as h bar. H over 2 pi, we just conveniently refer to that as h bar. And this is a new quantum idea. So, so let's just remind ourselves about angular momentum. So here's an electron circling the nucleus, which would be right here. And the angular momentum would be the radius vector cross product with the momentum. And so remember, the momentum is the mass, classically speaking, and he said that classical laws apply during these stationary states. Momentum is m times v. So our because this is a circular orbit, r and p are perpendicular to each other. So the cross product, the sine, the angle is 90 degrees. The sine of that 90 degrees is 1, and so we just get r times p, or r times mv. So the angular momentum would be mvr, and that's supposed to be a multiple of h over 2 pi, or h bar. So this was his new quantum principle, that from which the rest of his quantization of the we'll see the radius and the velocity and the energy of states, the stationary states within the atom, followed. Okay, so speaking of quantization, quantized radii and the Bohr radius. From postulate 4 and classical physics, Bohr derived that the radii of hydrogen orbits are quantized. And postulate 4 being the this one, that the angular momentum was an integer multiple of h bar, and then some classical physics relationships between force equals mass times acceleration and excuse me, Coulomb's law and so forth. So how did he do this? Well, he solved for the velocity of the nth stationary state in terms of, he solved this equation for velocity, so it would be nh bar over mr. And then he noted that classical, within that stationary state, classical laws would hold, and this is a form of F equals ma applied to an electron in a circular orbit, because this is Coulomb's force, E squared over 4 pi epsilon naught r squared. So F is equal to m times a. V squared over r is the centripetal acceleration of the electron in the circular orbit. Okay, so he basically had now an expression for V from classical physics, expression involving V from classical physics, and an expression for V in from his new quantum ideas of quantum physics. So then he just solved for V squared here in both these equations, set V squared equal to, solving this equation for V squared get you this, and here we just square all of these terms, and so we get this equation here, which involves just n, the stationary state number, and then constants, h bar, the new constant, Planck's constant, divided by 2 pi, the mass of the electron, the charge on the electron, and so forth, and the radius. And so from there, solving for the radius, we find that it depends on n and these other constants as n squared. So the radius of the nth classical orbit goes up as n squared. And we call this what multiplies n squared in this expression, we call this the Bohr radius. So it would be 4 pi epsilon naught h bar squared over me squared, the Bohr radius. And that's calculated here. I'm just putting in the values for h bar squared at 1 over 4 pi epsilon naught and m and e squared. And it turns out to be 0.53 times angstroms. And here's a picture of the Bohr radii quantized. So here's 1, here's 2, here's 2 with n equals n squared would be 4, so this is 4 times as the radius. This is not 3, so this would be 9 times that radius. And notice it also just shows a transition between states. That's postulate 2 for the emission of the photon. And it turned out conveniently that this combination of constants, which he got out of his study, was about the estimated size of an atom from other means in solid state physics and other experiments. So we have from this fourth postulate that the angular momentum is quantized, we have that the radii, there are certain allowed radii and certain allowed stationary states with those different radii in the hydrogen atom. And just to record different relationships here, this is again the formula for the orbital radius, and goes up as n squared. This is the formula for the velocity from above. It depends. It goes up as n h bar over mrn. So actually, it goes up if you plug in n squared a naught here in the denominator. The velocity would go as 1 over n, so it would actually get smaller as we go further out, which kind of makes sense. It's like Mercury, that it being the closest to the sun, goes the fastest, and then the other planets go slower and slower. And then finally, the energy, which can be found from the classical physics, is as e squared over 8 pi epsilon naught r, and here's r as a naught n squared. Okay, so we have quantization of these important physical quantities. Now to the problem of the spectrum of hydrogen and the matching of the so-called Rydberg constant that was involved in the Balmer formula. So using postulate 2 for the transitions between electron states and the quantized expression for the radius, which we just saw, leads to the formula that I just showed you. I just summarized. En is equal to e squared over these constants times n squared. And so we can call this e squared over 4 pi epsilon naught a naught, just call that e naught. And that would be since when we plug in n equal 1, for the lowest stable state, we would get an energy of minus E naught. So E naught is minus 13 point. So it turns out if you put in these constants, E naught is minus 13.6 EV. And so here are the states, minus 13.6 EV. Here is the, for n equal 2, we divide by 4, so we get minus 13.6 over 4, which gives us minus 3.4, and so on. They're all negative because they're all negative energies indicate bound states, and the electron is bound to the proton in the hydrogen atom. So what about the transitions, postulate 2? Well, we have that if we had a transition from a higher stationary state to a lower stationary state, we would have a photon HF with energy EU minus EL being emitted by that atom, and so we can put this in a certain useful form. We say 1 over lambda is equal to F over C. That's true because C is equal to F times lambda. And then F is equal to EU minus EL over H bar, and then that over C becomes EU minus EL over HC. And then using this formula up here, we have EU is equal to minus E naught over U squared, or NU squared rather, and EL is minus E naught over NL squared. And then, so we have a minus sign out in front, which we then distribute through. We wind up with this formula, E naught over HC, 1 over NL squared minus 1 over NU squared. And so 1 over lambda is equal to that. And that might look a little bit familiar. If you remember from when we looked at the spectral lines, the Balmer series, the formula which Balmer discovered was 1 over lambda is equal to a constant times 1 over an integer squared minus 1 over a larger integer squared. So we have exactly the same form coming from the Bohr model. So we can identify the constant here, the Rydberg constant, as E naught, the ground state energy, over HC, which if we write it out in terms of all of these constants, becomes this combination of masses and H bar and C's here. And that's equal to the Rydberg constant. And so Bohr had achieved his goal of deriving the Balmer formula from a set of principles, namely postulate 2 and postulate 4, which led to the quantized expression here. And this was the first plausible explanation of the Balmer formula. And this, when these constants were plugged in, the mass of the electron, the charge on the electron, and so forth, these agreed well with the value found experimentally for this constant, the Rydberg constant. So that's quite a success for the Bohr model. Okay, so the Bohr model has some quantum principles, some classical principle, one classical principle in it. It's kind of a mixture. But Bohr thought that any new theory of the atom should obey what is called the correspondence principle. And as he stated it, in the limits where classical and quantum theories should agree, the quantum theory must reduce to the classical result. And that's true because when we look around us in the world today, we don't see these quantum effects. We don't see big hops between energy levels of things. Things seem to be moving without granularity and smoothly and consistency. So the quantum world must blend smoothly. A quantum theory must blend smoothly into classical theory, when they overlap. That's what's meant by reducing to the classical limit, in the classical limit. So the classical, we can see this in one case. If we take this classical result for, if we imagine an electron orbiting in a nucleus with angular velocity omega, the frequency that it would emit would be omega over 2 pi. That's the natural frequency. And then omega is v over r, so because v is equal to r times omega for circular motion, so omega is v over r. And then using classical dynamics, we can substitute in for v and we have the 1 over 2 pi here. We keep the r, and this is v is just the we just get this from the Newton's law formula mentioned earlier. V is e squared over 4 pi epsilon naught m r squared to the 1/2. So we get this expression here just from using classical dynamics as we did before for v. And then since we know that in the quantum theory n is quantized, the radius is quantized according to this formula, which is a naught, the Bohr radius, times n squared. If we plug that in for r, this r in for this r here, we get some simplification, and we get this formula here. So this says that, classically speaking, at large radii, because for n large, the atomic radius would be very large. It goes up as n squared. The frequency which would be emitted would be this expression, going as 1 over n cubed. Okay, what about in the quantum theory? In the quantum theory, it's harder to get continuous radiation at a given frequency, like classical theory, but we can imagine a cascade of quantum transitions for large n plus 1 to n minus 1, down so forth, like 1,000,000 to 999,999 to 999,998, and so forth. And that's going to give off radiation, which will mimic continuous classical radiation by a circling particle. And so the prediction of quantum physics here would be that the Bohr frequency would be equal to the energy of those the energy of one of those photons that's being given off. And for n plus 1 going down to n, that would be the energy would be the final state minus the initial state being n plus 1, the final state being n, and then dividing that energy by h, because energy is equal to hf. Okay, then we do some algebra here and get a common denominator. So this is just some algebra, common denominator being n squared times n plus 1 squared, and then cross multiplying up here, simplifying on the top, and we get 2n plus 1 over n squared plus n plus 1 squared. But remember, we're talking about very large n here, because we want very big orbits. That's where the classical theory and the quantum theory should agree. Not when the atom is very closely packed. That's where quantum effects should be most important. So when n is very large, it doesn't matter much that we add 1 in the numerator, so this can become 2n, and this can just become n plus 1 is about the same as n. So this becomes approximately just e naught times 2n over h times n squared or n to the 4th, or 2 e naught over h n cubed. Okay, so we're almost done here. Then using our value for the ground state energy E naught, if we plug that in here, we find, if we plug that in here and simplify, we find this expression here, m e to the 4th over 4 epsilon naught squared h squared n cubed, which is the same one we got for the classical. Okay, so this is an example of the correspondence principle by looking at the quantum emission at large index of the stationary state, or what we call large quantum number, and the classical prediction, they should agree. So the Bohr model has a lot going for it. In fact, there's a couple more successes that it has that I haven't mentioned here. It's good at, it incorporates a so-called reduced mass correction to the hydrogen spectrum. We assume that the mass of the electron, we could just use the mass of the electron in calculating the hydrogen spectrum, but in fact, the electron and the nucleus rotate around each other, around a center which is not quite in the middle of the nucleus, but a little bit displaced. They rotate around their common center of mass, and that leads to something called the reduced mass. We can still treat it as a one-dimensional problem, but we use the reduced mass, which is the mass of the electron times the mass of the electron times the mass of the nucleus over the mass of the electron plus the mass of the nucleus. And you can see that, for example, as the mass of the nucleus gets really, really large, the denominator, compared to the mass of the electron, the denominator is practically equal to just big M, the mass of the nucleus. And then these two M's would cancel, and we'd get the mass of the electron. So it's the reduced mass is very, very close to the mass of the electron, but a little bit different. And then that is going to affect the mass that we put into the Rydberg constant here, and so it's going to affect the wavelengths that are predicted for hydrogen. And it was found with more accuracy when the hydrogen spectrum was measured with more accuracy that, in fact, this reduced mass reproduced the lines a little bit better than the mass, the mass of the electron itself. So that's good for the Bohr model. Second would be understanding of a deuterium line. And deuterium is a form of hydrogen which has 2 protons in its nucleus. So it's got a more charge, and I'm sorry, not 2 protons in its nucleus. It's got a proton and a neutron, rather. So it has more mass, and so with more mass, that's going to shift the mass that we use in the reduced mass here, and that's going to shift the lines spectrum, the spectral lines that we see. And it was found in 1932 when it was some of these visible lines, the alpha line in the Balmer series was looked at very closely, that it was a very, very small splitting, and that was due to a presence of deuterium, which again has one proton and 1 neutron, not 2 protons, as I said mistakenly. And a third success was the prediction of the helium ion spectrum. So a helium ion is, here's a helium nucleus, 2 protons, there's the 2 protons, and 2 neutrons, and then it would normally have 2 electrons, but in this case it's ionized, so it just has 1, so the net charge is +1, and that's a 1 electron atom, and so the same analysis can be applied to it with circular orbits and quantization of angular momentum and so forth. And the difference is here that in the energy here, we assumed that the energy was E squared, because this was the proton charge, which is the elementary charge, times the electron charge, which is the elementary charge. However, now we have in the nucleus 2 times E. So, and this, the electron would still be E. So this would be 2E squared over 8 pi epsilon naught Rn. So the energies involved in the helium ion are bigger by a factor of 2, and also the nucleus is more massive, and that's going to affect the reduced mass. But taking into account both of those effects, the Bohr model can handle the spectrum of the helium ion. Okay, so lots of good things for the Bohr model. However, also some limitations. It wasn't all the way toward the quantum model that will ultimately physicists were seeking. One, it only applied to single electron atoms, like the hydrogen atom, deuterium, and the helium ion. Efforts to apply it to the helium, the neutral helium with 2 electrons, didn't meet with success. It doesn't explain so-called fine structure line splittings. These were very, very fine little splittings in between of some of the spectral lines that were seen, and those turned out to be had turned out to involve a combination between something called electron spin, an intrinsic angular momentum of the electron, and the angular momentum of the electron around the nucleus. And that's not incorporated and wasn't able to be explained by the Bohr atom. It couldn't explain the intensity of the spectral lines. So in the Balmer series, some lines are brighter than others, but the Bohr model doesn't say anything about which lines should be brighter, would have more light, and which lines should have less. And finally, it can't account for molecular bonding. We know that 2 hydrogen atoms tend to bind into a hydrogen molecule, H2, but efforts to apply the Bohr model to account for molecular bonding, again, didn't meet with much success. So despite all that, the Bohr model accomplished quite a lot, and was a stepping stone between the classical solar system model and the quantum models of Schrödinger and Heisenberg that we'll be investigating in a couple weeks. And it explained the spectrum of hydrogen beautifully, and deuterium and the helium ion, and also accounted for the stability of the atom. And so in this transitional role, it played a key part in the introduction of quantum physics, so much so that Einstein said in 1947, the Bohr atom appeared to me like a miracle, and appears as a miracle even today. Not event today, but even today. So that's the Bohr atom. I hope you've enjoyed learning about it, and I will see you in class.